Hello and welcome to Math Magic. Today we've already been talking about exponential functions, and now we're going to explore some applications to the exponential functions. So first let's review what our common exponential forms are that we'll be using today. First we have the continuous growth decay model. This is represented by p equals p naught or p0 e to the plus or minus kt. And we notice that k will become positive when we are modeling continuous growth. However, when we are modeling continuous decay, we make sure we have a negative k there. T is our time variable, and that can be represented in seconds, minutes, hours, years, whatever we choose. The reason why we call this p0 or p naught is because that's our principal at the initial value. So whatever the substance or the value it may be, that's where it starts. And then after a certain amount of time, we have our new value of our principal. Next, we also have discrete decay growth model. Same type of, or similar setup, when we notice that we have our final amount with our initial principal here, or our starting value. We have this inside 1 plus, this is r equals our rate. And let's focus on the fact that that rate we have there is actually our annual rate. So that's something very important to check out when you are considering that this n here corresponds to this r as well. So if you have an annual rate and you compound it monthly, this n will be 12. However, if you have a monthly rate, then our n simply goes to 1, same as this n. So make sure you are keeping r in respect to our monthly rate. And then our t again is our time variable. So let's check out some few examples. Now let's consider ourselves software engineers. We notice that the amount of drive space that is used on a personal computer has been tripling every 6 months. We'd like to calculate the monthly percentage increase in drive space used, accurate to 2 decimal places. Now, let's first read this problem and check out where exactly we want to find our information from. So, reading, we notice that it has been tripling. So, from our initial value, we have 3 times that initial value at the end of our time period, which we notice t is 6, and also that's taken in months. So now we'd like to calculate the monthly percentage. So we're looking for our rate r, correct? So we set up our equality to be 3a is equal to a b to the 6th. Notice that our a here is our initial value, and we're going to have 3 times that initial value at the end of our time, 6 months. Now we simply can divide out our a's there, giving us a much simpler equation as 3 equals b to the 6th. B to the 6th is equal to our 3. That's the property of we can do through equalities, taking the 6th root of both sides or raising it to the 1/6 power. Since powers are multiplicative, we can eliminate that 6 right there, leaving us with just b is equal to 1.2009. Now recall that our b value is actually 1 plus r when we have a growth model. So since this is increasing every month, we have 1 plus. Make sure you note that if this was a decay model, this value right here would be minus. So make sure you are reading your questions very carefully and noticing that as well. So substituting our b for 1 plus r, we notice that 1 plus r is equal to 1.2009. Solving for r, and now we have our monthly rate at 20.09%, as we wanted to show. Let's try a discrete problem. If we invest $5,000 into a certificate of deposit for 5 years at an annual rate of 5.75%, how much money will be in the account if the interest rate is being compounded monthly? So right away we notice our initial investment is $5,000. So we're going to want to hang on to that one and call that P naught. So we ask ourselves, what's another variable that we notice? So again, we noticed 5 years, that is our variable T. And we're also given an annual rate of 5.75%. And then it asks us how much money will be accounted for. So we're looking for a total S. Again, here are our variables. Notice again that it was compounded monthly. So there are 12 months in a year. We use n equals 12. Recognizing that it's a discrete case, we will use this formula. Plugging in our variables, we get S is equal to 5,000, quantity 1 plus 0.0575 over 12 raised to the 60th. Computing that in your calculator, we get our initial value of $6,660.88. Let's check out another continuous growth. Consider ourselves biologists. A newly formed lake was stocked with bluegills 4 years ago. After 2 years, it was estimated that the lake contained 5,000 bluegills. And after 4 years, it was estimated that the lake contained 8,000 bluegills. If the bluegill population in the lake has been growing exponentially, then how many fish were initially stocked? Let's check out some variables here. So we notice after 2 years, we have 5,000 bluegills. And after 4 years, we have 8,000 bluegills. So now we just have 2 points on our graph with x value, or our t value of 4, and then 8,000. And then a t value of 2, and a value of 5,000 for a y, our dependent variable, correct? Again, we notice that our graph here, we're given 2 points at 2 and 4. We want to find our initial value times 0. So we're looking for this guy right here. We're able to set up the equation since we have continuous growth of 5,000 is equal to P naught e to the 2k, and 8,000 equal P naught e to the 4k. Notice that we are solving for this P naught. However, we have 2 variables in each one, so we need to solve for our k first. Using this equation, we are able to divide over e to the 2k, get P naught is equal to 5,000 divided by e to the 2k. Through substitution, plugging him right into there, we get 8,000 is equal to 5,000 times e to the 4k over e to the 2k. Notice that we can reduce these and turn them to 2 and divide over our 5,000, leaving us with 8/5 is equal to e to the 2k. And remember our rules for logarithms. The whole point of using logarithmic functions is to get powers usable. So let's take the natural log, since we have a base e here, to both sides. We get natural log of 8/5 is equal to 2k. Dividing our 2 over, and we get k is equal to 23.5%. Now that we have our k value, we're able to go up and plug into either one of these guys and solve for our final equation. Let's put it into our initial p0 e to the 2k. Remember that our decimal place moves over twice when we have percentage. Plugging this into your calculator, we'll notice that our initial value is actually 3,125 bluegills. I hope we enjoyed visiting some applications for our exponential functions. Please email me at alakai.copy@gmail.com. Thank you.